So you have all of the material properties. You have E in nu. And you have the tensions. Okay, yeah. Okay, so from the truss, you have the internal tension for each member.
Right, and that would just be like a 1/6 matrix of just one value, right? Like F over
Right.
A.
That's right. Yep. And so, but this is just the T value, you know? And so then what you know is the stress tensor is T over A, 0, 0. Where A is a variable. T isn't now. T is a number that you've calculated. And then this is a principal stress tensor. And so you know that the max shear is T over A minus 0 divided by 2. And you have some value that you're trying to keep that under, you know? And so then you can just solve for A.
Okay, so you don't even have to do the matrix.
Right. That's right.
Okay. Cool, thank you.
Mm-hmm. Any other homework questions?
This is more general, but when you're getting a strain from the internal tensor, do you do that calculation for like each cut?
Oh, so you calculate the internal loads.
Yep.
And then you're asking, okay, now you go to calculate the stress and strain. Yes, you either have to express those stresses and strains as your function of x and as functions of potentially y and z, because they'll change as you move around the cross section, or you just have to choose an individual point. I find that on the questions I give you, I tend to just tell you a specific point. Like in the example yesterday, I said, okay, in the x direction along the long axis of the beam, we're looking at the middle of it. And in that cross section, we're looking along the very top. Okay, so I'm telling you an exact point. For internal tension and compression, the stress doesn't depend on where you are in the cross section. It only depends potentially on where you are along the long axis of the beam.
Oh, because it doesn't change throughout the length of the beam, right?
It can, but not always, you know. Often, and a lot of times it's piecewise constant. You'll just have finite changes where there are external horizontal loads applied.
Okay.
But once you choose an X location, there's no change due to tension and compression as you move along the cross section. But with bending, it does change as you move up and down on the cross section. With shear force, it's going to change as you go up and down on the cross section. And when we talk about torsion, it'll actually change in every direction along the cross section. So I have to be pretty specific about what point you're doing. You know, if there's only stress due to tension compression, then I don't have to be specific about anything on the cross section. It's all the same. If there's stress due to bending moment, I have to tell you the height on the cross section. Shear force, I have to tell you the height And then torsion, I have to tell you exactly where on the cross section.
Okay, so, but in general, if a specific point
Oh.
isn't mentioned, it's just piecewise constant, like you said, just like,
If a specific point isn't, you'd calculate the internal loads to know whether it's piecewise constant. I know I give you 1 or 2 questions where you actually have to have y and or z in there as variables. Let's think about the example we did last time. So we had a 200 Newton meter torque and a 1500 Newton force. I guess we're not totally done with this yet, but we were saying the cross section looked like this. And we calculated the internal loads, and these were piecewise constant, so I can't use this as an example. I mean, these were actually not piecewise; they were just constant the whole way.
yeah, I guess I just mean, so like, a stress tensor for any given cut, assuming it's piecewise constant stress tensors,
Mm-hmm.
like you would just use the compliance matrix for each cut, right?
Yeah,
Like assuming just pure tension and compression, like
Right.
as simple as possible.
that's right. That's what you would do. Correct.
Okay, I
Yep.
just wanted to make
Okay,
sure.
right.
So like for the one, I mean, like at least in some of the homework, it'd be like each one had 3 stress and strains, right? Like if there was like 3, if there was like 2, if there was 3 cuts,
Oh yeah,
there'd
there's
be
3
stress,
tensors,
yeah,
yeah,
3
3
tensors,
stress and
3
strain
strains.
tensors.
And then for the ones with 2 materials, it was 6.
Oh yeah.
Yeah.
I may or may not have just forgotten to do those.
Okay. So remember, exam 2 is next Friday. And the topics are up through stresses due to bending moment. So today we'll probably start talking about stresses due to shear force, but that won't be on the test. Any questions about the test? Okay, so let's go back to the example from Wednesday. So we have this cantilever beam. It's 1 meter long. We have this external moment of 200 Newton meters, this compressive force of 1,500 Newtons. And we want to calculate the stress at the midpoint this way And then on the cross section, at the top of the cross section, we want to first calculate the stress tensor for the square cross section. And then second, calculate the stress tensor for this T-shaped cross section. Where this is 0.5 meters, this is 1 centimeter, this is 1 centimeter, and this is 0.5 meters. And the key thing to recognize here is these two beams use the same amount of material. Okay, so last time we did part A. And we got that the stress tensor was negative 1.3500 megapascals.
Is that just for the tension?
That's both. And now we're going to do part B. What we know from the internal loads calculation is that the whole way, and at the point we care about, the internal tension is negative 1,500 newtons. And the bending moment is positive 200 Newton meters. Okay, so first, due to internal tension, tension compression, sigma xx is equal to negative 1,500 divided by the area. The area is the same as it was last time, the area of the cross section. So that's negative 0.15 megapascals. And so the stress tensor due to internal tension compression is negative 0.15, zeros everywhere else. But now we want to see about the stress due to the bending moment. And here's where we're going to get something different. Okay, so for this cross section, we already calculated the location of the centroid, and we already calculated the area moment of inertia. So first, let's think about the centroid. This is where the neutral axis is located. And that centroid, which we had to figure out to calculate the moment of inertia about the neutral axis of the whole thing is so the whole thing is
2.709 times 10 to the minus 4. 2.709.
well, let's see. So we have here's what we know because I used down here as where my origin was. So this distance is 0.3775. And so the distance from the top, the whole thing is 0.51. So this is going to be 0.51 minus 0.3775. And is that what you said before? Is that what you just told me?
Should be 1.325.
No, I would have told you the moment. It's much smaller.
So this green distance is 0.1325.
Crazy. If you wouldn't have said that was green, I would not have known.
Really?
Mm-hmm.
Oh, wow.
I'm red-green colorblind.
Oh my gosh. Okay. Well,
Anyway.
I guess I should choose different colors to do my.
It's very common.
That's a real bummer while you're driving. I guess it's not too hard to memorize where on the.
Well, I can,
What if they turn the stoplight upside down? You'd be screwed.
No, it's like with the like neon fluorescent colors, it's very obvious.
Oh, okay.
It's like only certain shades.
Oh, okay. Huh.
Sorry, officer, I can't tell the colors.
That's a good idea. Oh my God, you're immune to arrest. You can do whatever you want.
All right, I'm gonna try that.
Pull out the colorblind color. Read them and weep.
All right, so we know that our XX stress element is negative my over I. And we calculated that our I is 2.709 times 10 to the minus 4. And so now we can plug all this stuff in. So sigma XX is equal to negative of 200. Our Y goes from the neutral axis to the height that we care about. So that's 0.1325. We're dividing by 2.709 times 10 to the minus 4. And we get a value of negative 0.098 megapascals. Okay, so the stress tensor due to bending is negative 0.098. Got zeros here. And so the total stress tensor is the one due to tension compression plus the one due to bending moment. So negative 0.24800. Okay, so compare the stresses in these two beams that are made out of the exact same amount of material.
Is this one more?
No.
Did I write the other one wrong? Oh, 0. Okay, yes, okay.
Yeah, it's 1.35 compared to 0.248. So with the same amount of material, with a careful choice of what the cross-section is, we reduce the amount of, we reduce the amount of stress by almost a factor of 10 or, somewhere in that ballpark. And what that means is we can apply a ton more load to it before we're worried about permanent deformation or anything like that. Okay. So just by organizing, that's a terrible word for what I'm talking about, building the same amount of material into a different cross-section we got a huge decrease in stress. Any questions about that? Well, I mean, this is actually like a real shape of beams that are used, and there's a reason for that, and the reason is this. Okay. So next is stress due to shear force. So remember, here's where we are. Our total stress tensor, because of the superposition principle, is going to be the stress due to internal tension compression plus the stress due to the bending moment plus the stress due to the shear force plus the stress due to the internal torque. And we can deal with these two. Before I go on to shear force, can anyone remember what the restrictions on the beams are for bending moments? This is really, it's not as key in a class, because for the most part, usually, because you're going to be given conditions that work. But if you're out there and someone asks you to calculate a stress and you look at it and you calculate a bending moment, like you have to know whether you can use the tools that you're planning to use, So what are the beam restrictions?
Was it that it has to have a consistent cross-section?
Yes, that's right. That's the first one. There's 3 of them.
Same material for
that? That is required for everything in this whole class. That's homogeneous.
The beam has to be straight.
Straight, yep. Or nearly straight. You can fudge that a little bit, but not too much. And then there's symmetric about the y-axis. So you can do the cross-section can be the Star Wars communicator symbol.
Star Trek.
Oh, that's what I mean, Star Trek. But it can't be this.
Once you turn on its side,
Yeah.
Yeah, and you can't turn it on its side.
not allowed.
Right. So we can do, yeah, triangular things if they're oriented the right way. We can do rectangular things. We can do circular things. Those are all fine. Okay, now we're going to get into the most stringent restrictions, I suppose. So first, let me illustrate what the stress due to shear force looks like. So here is a beam. And so the coordinate system that we always use has the x-axis this way, the y-axis this way, and the z-axis this way. And so let's think about so if we're trying to calculate stresses along that's green. I'll just tell you what colors I'm using. If we're trying to figure out stresses along that cross section, here's what it looks like. This is a whole line of stress elements. Okay? And the shear force, are you with me on what I'm trying to draw there? That's just like one infinitesimal row of stress elements on this cross section. And if you think of this cross section, if there's a shear force on that cross section, a positive shear force would be like downward forces along that face. Okay, remember that's what a shear force looks like. So the stress produced by that downward force would look like this. Okay, so on a stress element, that would be a force, a stress like this. And then it would have to be like that too. And if we look at these stress cubes straight on, where z is this way, x, y, these would be a downward stress there, one like this, one like this, and one like this.
Is it normal to draw them that way?
I'm just not, I don't do it very often, but just remember that every face is the opposite of its opposite face, you know. So I'm just doing that to make it clear that we have this stuff going on over here too. But the bottom line is, so a shear force produces an XY shear stress. Okay, but remember that you can, by just reasoning out the directions of what's going on, like by thinking about a figure like this and what a shear force is, you can make perfect sense out of the fact that that's an XY shear stress. Okay. All right, and if a positive shear force is down and leads to those stresses, okay, that means that we're gonna have a negative relationship between the shear force and the shear stress, and that's where the negative comes from in this formula, when we get to it. Before I give the formula, let me give the beam requirements. So the beam requirements for the stress due to shear force and this one is very restrictive. So we only have two possibilities. So either it's a rectangular cross section, with the height bigger than the base, or it's a circular cross section if that was the end of it, that would be that's pretty horribly restrictive already. But if it's a circular cross section, we can only do this at the neutral axis.
So does that mean it has to be like a solid circle?
No. It can be a hollow circle.
So what happens if you had forces that would cause a shear stress in a material with a cross section that doesn't?
We just don't have a way to calculate it.
So we just say it's zero in our little like stress tensor?
No, no, you just say I can't calculate it, you know?
Okay.
Yeah,
With these tools.
right, correct. It just gets a lot more complicated. All right, so you can, if you have a rectangular one where the height is bigger than the base, you can calculate everything. If you have a circular one, you can only calculate it at the neutral axis. Well, what good is that? There's one thing useful about that. At least that neutral axis is where the stress due to shear force is biggest. Okay, so all that stuff about Star Trek communicator shapes and all this cool stuff, we could do calculations for bending moments. If there's shear force present, all that is thrown out, and all we can really do is rectangular, you know? I mean, or we could do circular at the neutral axis. But the problem with a circular cross section only doing the neutral axis is, okay, that's where the stress due to shear force is biggest, but that's where the stress due to bending moment is zero. So there's important stuff going on at other places on the cross section. So this is a real problem. Anyways, that's why you want to remember these restrictions. Basically, when when we get through all of these, the only things we'll be able to calculate if all of these external loads are present are rectangular thin-walled cross-sections and circular cross-sections at the neutral axis. So we're going through all this work, but we're pretty restricted in what we can do every calculation for.
So is it just like right to finite elements then?
No, there's other ways to do it.
Calculus-y ways?
Yeah.
Okay, I got an exam. Have a nice weekend.
Okay, good luck.
What class?
Fluid mechanics?
Oh, God. Good luck.
Thanks.
Okay, so that's the deal with stresses due to shear force. But if these criteria are met, the XY stress due to shear force tau XY is equal to negative shear force times this new thing Q that we're going to calculate, divided by the I that we've already talked about, times B. This Q, we still need to define that. This B is the width of the cross section. At the desired height, on the cross section. And I is the area moment of inertia. Okay, so before we can do calculations, we have everything already that we need except that Q. So I have to tell you what that is. And it's something like the third area moment or something, but I'm just going to call it Q. But here's the definition. I think the easiest way to define it is just with a picture. So let's say that's our cross section. And this is the neutral axis. And let's say that this is the line where we want to calculate the shear stress. Okay. Then the area above this line has a centroid. So I'm going to represent that like this. Okay, that's the centroid of this area. The distance from the neutral axis to this centroid of this area, I'm going to call D. The red is the area A. And if you can internalize all that stuff, then Q is just the area times that distance D. Notice this is always positive. Here is a cool factoid. I don't know how cool it can be having factoids about engineering, but the way I have this drawn, I calculated everything using an area above my desired line where I want to calculate that stress. So Q using the area above the desired line always equals Q doing the same thing, but with the area below the desired line using area. That's just like one of those surprising mathematical things. So if it's ever easier, if for some reason it was easier to calculate the area, the white area, and the centroid of the white area, you can do this formula that way too.
Would the D then be still up to that upper centroid?
It would be to the, no, it would be to the centroid of the lower one.
Okay, so you can just do like any cross section?
So there's always a line where you want to find the values, and that's this. Okay, in this case.
Okay.
Okay, and then so you can either figure out the red area and the centroid of the red area and use this formula, or you could figure out the white area and the centroid of the white area and use this formula.
How do we know what the line that we want to calculate is?
That's given in the problem. Yeah. One other thing about this, I said that, so it seems pretty useless that we can only calculate the stress due to shear force for a circular cross section at the neutral axis. But this Q value is always biggest at the neutral axis. Okay. You see how that could be? You have this big area, half of the area of the whole thing. You have a distance to the centroid of that half of the shape. And so that Q is always biggest there. And that's why the shear stress is always biggest at the neutral axis. Okay, so let me draw a picture of this. So let's say we have a, what the, work, damn it. Okay, so let's say this is our cross section. And this is our neutral axis. And this is where we want to calculate the stress. So these are the two ways we can do it. We can calculate this area and this centroid. Or we can calculate this area and this distance to the centroid. And those are always the same. So these give the same answers. Any questions about that? Okay, so on Monday we'll do some examples. That is all. Have a good weekend.